There we go. And yeah, do you want to say a few words before we kick it off?
Yeah. So the first session of the Isogeny Club. Welcome everybody. We hope to be able to provide a bit of an informal session, and that's also actually the goal of the Isogeny Club, to have a bit of an informal group that, where on the other hand, like young PhD or postdocs present their work, and on the other hand, the young PhDs and postdocs join in and can follow along and ask stupid questions that you're too afraid of to ask at like Eurocrypt or so. We also have non-young isogenists in the room, I think. That's also fine, you're very welcome. But be aware that some of the material might be, I don't know, a bit boring if it's stuff that you've already heard before or so. So the target audience is young isogenists, and but everybody is welcome to join in. The talks are recorded if the speaker wants to. So today we have a recording, and we will put that online on the YouTube channel afterwards, so you can watch it back if you have to go in the middle of the session. Jonathan, did I miss anything that I should still say?
No, I think we briefly discussed like whether we should have some other arena to discuss things as well, like Discord or something like that. On the one hand side, it's very nice to have like this type of channel to discuss things, but on the other hand side, there already exists lots of these channels and arenas. So yeah, if anyone has any ideas or comments related to this, please just, send us a message or even shout out now. Yeah.
And I should mention that we're now also on researchseminars.org. So you can save us there or copy the invites to your calendar, and then it will automatically sync up over there. Yeah, Zulip is also a good suggestion. And we were thinking, so Discord, bring up a Discord or a Zulip. So we'll see how it turns out, what the interest is of people, and then decide what we will do. So we hope that the Isogeny Club will help a bit for young PhDs or starters to get to know some people and some names, and to, I don't know, if you've been at a conference and you meet some people, then at least you can talk about Isogenies. And I think with that, we can go to the first speaker. I don't think he needs a lot of introduction after this summer of Isogenies, Thomas Decru, and his work together with Wouter Castryck on breaking SIKE may have ruined some holidays this summer, or I don't know, it was an exciting time for everybody, I think. Today he will have, I think, his first public talk on how, together with Wouter, he broke SIKE, but also a bit more on the general setting in Genus 2, where this attack comes from. So Thomas, the floor is yours.
Okay, thank you. Can everybody understand me properly? I hope so. And see my screen. So I'm going to be talking about breaking SIKE. Crane and Jonathan already asked me a couple months ago if I wanted to give a talk. The goal was to do radical isogenies unless something more interesting popped up. So I guess we're here now. As Crane said, this is joint work with Wouter Castryck. He already gave a talk about this at ANS, by the way. So this is going to be a little bit less formal and a little bit less mathematically heavy, I guess, but his talk is on YouTube as well, if there's still some details that you want to check before going into the paper. So today I wasn't really sure what the target audience was going to be. There's a lot of people here. If you have questions, there's like 60-ish people here. By all means ask. I don't think I get notifications by chat, so just interrupt me, I guess. Okay, so somebody in chat. Okay, YouTube link, that's fine. So I'll be talking about a little bit broader, as Crane said, about how we broke SIKE, and there's going to be 3 parts. I'm going to give a broad overview about SIDH and SIKE, because I'm guessing there may be some post-quantum people who are isogeny enthusiasts here who are not really sure yet if they want to continue the topic of isogenies. And the second part is going to be isogenies in dimension 2. Not all of the material that I'll cover there will be necessary to really understand the attack, but I think it tells a good story about how we found the attack, at least. Hold on, there's more in chat. Okay. I do get notifications from chat, so if you have a question, you can post it in chat as well if you don't feel like talking. And then the third part is going to be like the glue and split attack. You'll see why the name, where the name comes from the end of the second part. And in between the parts, I'll like ask if there are any questions. But as I said before, feel free to interrupt me. Okay, so we'll start with SIDH and SIKE. So for the mathematicians, I'm going to be a bit more hand-wavy, but if you like isogenies, then they're simply surjective group morphism with finite kernel. Now, I felt it was a bit weird to have an Isogeny Club meeting where I never really, or like, some people may not know what an isogeny is, but it's really a map from an elliptic curve to another elliptic curve. So let's say E and E prime. And I remember, I think Luca de Feo did something similar like this once, where he actually plotted an elliptic curve over a finite field and like actually showed what an isogeny looks like as well. So it's a map typically denoted by some Greek letter phi from one elliptic curve to another. And if you want to write it down with some polynomial equations, it looks something like this, right? You have some rational functions here, and you have 3 points that are mapped to infinity. These are the kernel points. And then the isogeny, it's a separable isogeny, so the degree is just simply 3. And if we would actually write it out, you could see that every point here on E prime actually has 3 pre-images from E. So each point here has 3 pre-images, the degree is 3. Now in general, isogenies, well, you can represent them the way you want, right? You can write down the entire kernel, and you can derive this equation from it as well, or vice versa. You can take, well, these polynomials are not really independent, so you can take certain polynomials of here to represent an isogeny. But in general, the higher degree isogeny, obviously, the more complex your not per se your representation will be, but the more complex your computations will be when you evolve them, when you try to evaluate them, or just even sometimes evaluating the codomain or finding a codomain. So this gave some like rise to some cryptographic schemes, because there's a general hard problem. If you are given 2 elliptic curves, it's hard to find an isogeny between them, any isogeny. This is the generic version. Obviously, you're going to need enough elements in your field for this problem to be actually hard. You're going to need the degree of the isogeny to be high enough for it to be hard, and so on. Sometimes you need more info, sometimes you need a specific degree isogeny, and so on. Given that, like, we're looking for new post-quantum crypto schemes, this is a pretty good hard problem to consider. And then some cryptographic schemes popped up. Again, since this is the first presentation of the Isogeny Club, I kind of wanted to maybe try and give a top 5. I don't want to offend anyone who has a scheme is like, oh, I deserve to be in the top 5. But for me, this feels like some sort of, if I had to pick 5, I think these are sort of the choices that I would make. Like CRS is the one that originated, which is like the, well, maybe some people don't know it yet. C-side is more well-known, I think, nowadays, but CRS is basically C-side, but with ordinary elliptic curves. In 2006, we had the Charles Gordon-Lotter hash function, which has this similar framework as SIDH by Zhao and Feo. And then pretty recently, we have SKI-sign, which I think is promising in a way, but it's still very recent, and I'm not sure. I think they're at like 1 second-ish or something signing time, but I mean, it's been like only 2 years really. So there's still a lot of room for improvement there to actually make a really cool signature scheme from Isogenies as well, right? So the attack by Wouter and myself only really applies to SIDH from this list. So Isogeny-based crypto is far from that, I would say. Also to some related schemes to SIDH, like B-side and SETA you have as well, if I pronounce that correctly, and some other schemes as well. But the other ones, like C-side and SKI-side in particular, are really not susceptible to the attack for reasons that will become clear later on. Okay, so SIDH, super singular isogeny Diffie-Hellman. If there are cryptographers here who don't really know what isogenies are, then we have Alice and Bob always, who want to exchange a key. Now, obviously, we do this in a Diffie-Hellman type of way, and we pick a super singular elliptic curve. over some finite field fp squared. Why do we take supersingular elliptic curves? Without going into much detail, they're kind of nice to work with. You can define them over fp squared. All the isogenies end up in elliptic curves over fp squared as well, and so on. It's easy to control the amount of points. There's other criteria as well. And then Alice and Bob both take a secret kernel. Alice takes some kernel in the 2 to the e torsion, Bob in the 3 to the f torsion. They compute an isogeny, and then Alice sends her new elliptic curve to Bob, and Bob does the same with his new elliptic curve EB. Obviously, this is like a problem, because in the Diffie-Hellman type of scheme, like Alice now will want to apply her GA kernel to compute an isogeny starting from EB, but what the hell is GA on EB? Regardless of how Alice like represents GA, like whether she does it with like a kernel generator or kernel polynomial or whatever, like none of these things can even be interpreted on EB. It makes no sense. You can't really do anything with this. So you need to slightly adjust it in the sense that you also need to give a basis of the 2 to the e torsion and the 3 to the f torsion. And then they have to generate their kernel for something like this. I mean, you can replace RA by 1 here. I guess that's not an issue, but I think this was the original scheme. And then instead of just sending through the curves EA and EB, they also send over the images of the other parties' basis of their torsion under your own isogeny. So Alice gets EB, she gets the images of PA under Bob's torsion and the image of QA under Bob's isogeny, sorry, not torsion. Now why does this work? Because then Alice can compute this isogeny phi prime A, which is simply the same kernel, like with these scalar multiples, but then applied to the images of her torsion points under Bob's isogeny. And this works because Bob does something similar, and then you have 2 elliptic curves which may not be identical, but they're isomorphic. So that's enough to have a shared secret, namely the J invariant, right? So they can exchange a key like this. But to even make this work, you really need like these images of these torsion points. And it's always been some sort of suspicion in the sense that if SIDH would get broken, then these torsion points would probably be the clue, because in general, finding isogenies between elliptic curves, supersingular or not, seems to still be a hard problem. And people are more and more convinced of that, with good reasons, I would probably say. But these torsion points then were indeed the killer. And any other isogeny-based crypto scheme which involves sending through torsion points will either be broken or should be is possible to be susceptible to our attack. Okay, but the general security of SIDH is a bit complicated in the sense that, well, there's a blog post by Daniel Bernstein. I don't know too much about quantum computing, but there's a lot of, well, I don't want to say vagueness, although I did type it out here, but still, I mean, it's not as easy as classical security, right? Sometimes you need like your classical computer to interact with your quantum computer and stuff like that. There's circuit depth, there's other costs. It's not as clear as classical security, but nonetheless, like asymptotically, the best generic attack is the claw finding algorithm with P to the power 1/4 classical, if I'm not mistaken, and P to the power 1/6 quantum. In 2017, I think, there was torsion point attacks on unbalanced parameters 2 to the E and 3 to the F. What do I mean by unbalanced? That if 2 to the E is much larger than 3 to the F, or vice versa, it doesn't really matter, then SIDH was already broken. Nobody really initiated SIDH in that way, I think. At the very least, SIKE wasn't initiated like that, so nothing was broken, but it's not like SIDH was like that didn't have any flaws. And like the torsion point attack, I think the first was by just Christophe Petit, and the follow-up work was with a bunch of authors. I'm not gonna try naming people because I will forget people and I don't want to offend anyone. But anyway, our work is then a heuristic polynomial time algorithm to break SIDH, even with balanced parameters. And we also need some pre-computable integer factorizations. These weren't really a bottleneck, even for like nest level 5. They could be done on a regular computer, really, and there were no issues there. But especially in a quantum setting, this doesn't even matter, these pre-computable integer factorizations, because they're just inherent to the system and not to the SIDH setting itself. Oh, I probably didn't mention that, but I'm definitely only going to talk about our work. There's been some follow-up work, both in the terms of attacking SIDH as well as trying to fix SIDH, which like to mask SIDH, but I'm not going to be talking about that because I don't feel comfortable talking about that, and maybe other people will want to mention that at one of the next week's Isogeny Club talks. Okay. And now what is SIKE? Well, SIKE is super singular isogeny key encapsulation. Thing is, if you take a static key SIDH, like there's some chosen ciphertext attacks against it. What does this mean? That you can't really use a long-term public key unless you like use some sort of encapsulation for it. This isn't really too much of an issue. I'm not going to go into technical details about this. Basically, SIDH is like the very basis of SIKE, and then just SIKE builds a key encapsulation on it to allow a long-term public key. Okay, so for the mathematicians who are curious, like about the size of the field that we work over, there's a question. Aha, okay, Lorenz. Okay, that's a fair point. Yeah, that's true. So Lorenz is definitely one of the authors. Feel free to name all the authors. I mean, Christoph is also part of the attack on the torsion points. So what Lorenz said in chat is that, where can I go back here? So this, the 2017 torsion point attack, I think then it was only in 2019, I want to say, or 20 or something, that there was actually like the attack was round with like, I think there was like 5 or 6 authors, including Lorenz Pony, Christoph Petit, Dekehen, or how we pronounce it. So the work in 2017 from Christoph Petit didn't break anything. Sorry for that. Okay, so for the mathematicians, like the sizes of the field we work over is huge, right? I mean, in general, we work with a field P with characteristic 2 to some power times 3 to some power minus 1. I mean, the amount of primes of this form isn't like huge, but there's definitely like, we're not running out really. So we definitely have some viable things that we can use. And the starting curve in SIKE is always this curve for some technical reason that I don't want to go into now. The reason why we use primes of this form is simply because the super singular elliptic curves then have 2 to the e times 3 to the f squared points over fp squared. This means that we can easily compute rational torsion, rational kernels, rational isogenies, and so on. All the arithmetic happens over fp squared then, and we don't really have to do anything special in that regard. Note that for all these values, 2 to the e, 3 to the f is similar in size. I mean, obviously, to make a prime like this, you can't have them as close as possible per se, but they don't really differ by a factor of 2 to the 10 or something, as far as I'm aware. So Alice and Bob have similar entropy in the sense that they have a similar amount of possible elliptic curves that they can reach as key that they want to exchange, but also that the torsion point attacks on the unbalanced parameters don't really apply to SIKE. So SIKE was not broken from the torsion attack, the torsion point attacks. Now, one final thing, which I think, well, is inherent to our version of the SIDH breaking, which we've been notified by multiple people very shortly after posting it on ePrint that you don't really need to do it. But there's a difference between the computational and decisional isogeny problem. Okay, so the computational isogeny problem is that if you're given 2 elliptic curves, E and E prime, find me an isogeny of, well, in this case, degree L to the K between. In SIDH, it's L to the K, and C side, it can be a product of many small primes. But let's focus on L to the k right here. However, if you also have a decisional, you also have a decisional problem, right? So given E and E prime, does there exist an isogeny of degree L to the I between them for I ranging from 0 to k? 0 and k can be excluded, it doesn't really matter much. Now these problems are related. Maybe that's something that I'm guessing mathematicians have less, at least the mathematicians I talk to have less experience with, I guess, to think about something like this, but they can be easily translated in some way, at least in our setting. Why? Because if you have an isogeny of degree L to the k from E to E prime, for example, and let's say you have an oracle which can answer the question to the second problem flawlessly in some sort of in a limited amount of time, then it's really easy to reconstruct the entire isogeny, right? Why? Well, an isogeny like this is always computed just by concatenating k isogenies of degree L. So for this first step, E1, there's L plus 1 options, at least in the SIDH setting. You can see side, there are only 2 options, but whatever. And L is a small prime, so the amount of options here is limited. Like for Alice, there's only 3 options. In the SIDH setting, for Bob, there's 4, so that's not a lot. Now what you can do is you can just, like for Alice, 3 options, you can ask the oracle, well, is E1 L to k minus 1 isogenous to E prime? And with overwhelming probability, only one of them will be correct, right? Because the chance of 2 of them being L to the k minus 1 isogenous is non-existent pretty much, as long as you work over fields of cryptographic size. So by just asking the oracle 4 questions, or even 3 questions, because if the first 3 fail, the 4th one will have to be correct, you already know the first step in the isogeny chain. And then the next step, you only have L options because, well, you never take the dual isogeny. And you can ask the oracle again, okay, which one of the possible E2s is L to the k minus 2 isogenous to E prime? So up to some constant factor, I mean, as long as you have, okay, Tanya prefers tulip over Discord. So up to some constant factors, these are really, I mean, these are polynomially equivalent, at least in this setting. There may be some other things that apply. And in fact, you don't even need to have an oracle that can answer it for all I. It's okay, like, let's say you have an oracle that can only answer this question for even I, then you can just, well, there are L plus 1 times L options for E2, so you just will need to ask a little bit more frequently, right? Like, is E2 L to the k minus 2 isogenous to this, then E4, and so on. So as soon as you can answer the larger of these, this will break the computational version of this isogeny problem as well. So this is something that we really used in the in our attack, which was not needed apparently, but I still think this is an interesting property about isogeny computations in general, so I definitely wanted to include it. I think this is the last slide of my first part. I'm not sure if anybody has any questions. Okay, if not, then I'll just continue. All right, isogeny in dimension 2. Isogeny in dimension 2 is actually pretty cool. Wouter and I wrote some stuff about it previously, including with Ben Smith, at least. I think just Ben Smith. So first, before we talk about isogenies, obviously we need to talk about like the objects that we're working with, because an elliptic curve is not a 2-dimensional object. And in general, the generalization to dimension D or G, whatever, is called an abelian variety. In dimension 2, these are called abelian surfaces for obvious reasons. Personally, I also think elliptic curves should be called abelian curves, but that's not going to change anytime soon, I'm afraid. And typically, if you don't know which type it is, you just write it with a capital A. At least the literature does that, but it does as well for abelian varieties. Now, which type? I mean, in dimension 1, you just have elliptic curves, right? I mean, you can have some sort of different representation of elliptic curve that, I mean, at first sight, it doesn't look like an elliptic curve, I guess, but in practice, it's isomorphic to an elliptic curve because any 1-dimensional abelian variety is isomorphic to an elliptic curve. But in dimension 2, you have 2 types of abelian surfaces. On the one hand, you have products of elliptic curves, just E times E prime. And on the other hand, you have Jacobians of genus 2 curves. See, so this is a hyperelliptic curve of genus 2. I'll talk about that in a bit. But the products of elliptic curves are really easy. You just work on it component-wise. So you have E times E prime. It's just a point on this surface is basically a point on this curve and a point on this curve. So it's really easy to compute. If you want to scalar multiply a point on this abelian surface, you just scalar multiply a point on this curve and on this curve. Sometimes if it's confusing to read paper, I guess some people talk about points when they mean pairs of points. I mean, they're all points, I guess. But when talking about Jacobians of genus 2 curves, again, an element in this Jacobian is often called a divisor, or sometimes also a point of the Jacobian, but it consists of 2 points of the genus 2 curves. So in that sense, they're actually equal, that you sort of generically you'll need 2 points. There's some degenerate cases here as well, but I'm not going to go into depth about that. So some remarks, some rather important remark. We're actually interested in principally polarized abelian surfaces. If you want to learn more about that, I could say maybe Ben Smith's PhD thesis, maybe somebody will give a talk about that. Crane, if you know one of the PhD students or something who wants to give a talk about that in the Isogeny Club, by all means, I think it's an interesting topic because it's mathematically less intuitive than a lot of the elliptic curve stuff. The thing is, if you don't have a principal polarized, if you don't have a principal polarization, you can't really do anything. Because if you don't have that polarization, you can't even write down an equation, which is sort of silly. Obviously, it does not allow you to do any sort of cryptography or mathematics, well, abstract math, yeah, but nothing practical. So we need this principal polarization. I'm going to mention that on the cases where it's relevant, but I'm not going to go into detail about the definition or anything. But this allows us to sort of write down the curve equation C here. It looks sort of like the generalization of an elliptic curve, right? Instead of degree 3 equation in X, we have a degree 5 equation. You can replace it with a degree 6 equation as well. For certain formulas, the degree 6 version is actually a lot easier. There's some subtleties between the two, but in general, you can think of a Jacobian of a genus 2 curve like this. This is an image I think most people recognize what I'm trying to point out here. This is really the chord tangent law, right, on an elliptic curve. So the teal line represents an elliptic curve. To add P and Q, draw the line, flip it about the x-axis, and boom, you have P plus Q. Now, is there an analogy between products of elliptic curves and Jacobian of genus 2 curves in the elliptic curve setting? An analogy between products of elliptic curves and Jacobians of genus 2 curves and I don't think yeah, the products of elliptic yeah, in the graph setting, as Hendrik Florit says. So the question is if there's an analogy between products of elliptic curves and Jacobians of genus 2 curves in the elliptic curve setting. And then the suggestion is maybe something like elliptic curves over FP or over FP squared. And then Hendrik Florit answered in the sense that products form a distinguished subgraph. That's like what Hendrik says is probably the only thing that I can really envision now in the analogy, that indeed it's a subset, I guess, like the products of elliptic curves are a subset of the abelian surfaces, just as the elliptic curves over FP are a subset of those over FP squared. And if you want to, like, I didn't really draw graphs, but if you want to envision them graphically, you could sort of distinguish a similar thing. I presume it is not a connected subgraph. Well, that's something that may surprise you, actually. And Remy has something else to say. The thing is, the products of elliptic curves, if you like look at generalization of the isogeny graph, is like super highly connected. And I think it would actually, I mean, my intuition would say that it's definitely connected. Yeah, it will definitely be a connected subgraph, the products of elliptic curves. We'll come back to that later. And then Remy says that pairs of elliptic curves are really a natural border of genus 2 curves. Yeah, that's also true. But before I'll come back to that, how do the points look on E? We'll also come back to that. The points on E times E prime basically look like just take a point on E, take a point on E prime, boom. Just like working in the XY plane, you basically take a point on the x-axis, you take a point on the y-axis, and then boom, you also have something, right? So just write it down like component-wise, just like open bracket, P, comma, Q, close bracket, with P on E and Q on E prime. That's a point. Yeah, maybe I should have typed that, what Lorenz said, obviously. It's really component-wise. It's not, I mean, just think about it as the plane, but your axes are now elliptic curves. That's really it. Okay, so the reason I've wanted to show this picture is, well, because because I assume you don't know the picture, because otherwise I think you would have like logged out already by now. But because there's a clear analogy with the Jacobians of the genus 2 curves, right? So here you have a point P, a point Q, then third point of intersection, flip it about the x-axis. Now, as I said, on the genus 2 curves, to consider an element in a Jacobian, so like a point in the Jacobian, a divisor in the Jacobian, whatever, it consists of 2 points on the hyperelliptic curve of genus 2. So P1 and P2 is a pair of points consisting of 1 element in the Jacobian. Q1, Q2 is a pair of points on the genus 2 curve, again, which is 1 element in the Jacobian. And as well, we have 4 points now instead of 2. So obviously you can't draw a line through 4 points. Well, most of the time you can't, but you can draw a unique cubic through this. And this is actually the perfect geometric analogy. And then you have 2 new points of intersection, R1 and R2. And if you flip these about the x-axis, well, this pair of points is actually the sum of P1, P2 plus Q1, Q2. I mean, again, there's some degenerate cases where this doesn't apply, obviously, but the same is true in elliptic curve case. But you can draw it. I mean, the generalization is not too hard. It's only if you go to dimension 3 or 4 with prim varieties and whatnot that things start to get really weird. But as long as you're working with Jacobians of hyperelliptic curves, things behave rather okay-ish, I would say. Now, SIDH, as well as a lot of the other isogeny-based cryptographic schemes, works with supersingular elliptic curves. Does something like a supersingular abelian surface exist? Yeah. And the thing is, elliptic curves are easy in a lot of ways. And if you want, you can write, I mean, there's a lot of people here, right? How many people? We have 70 people here. If I would say, give me the definition of an elliptic curve that is supersingular, I would say that the first one would probably be the most common one, but it would definitely not be the only characterization that we see. You can even go on Wikipedia, there's like a list of like a dozen different characterizations that you can have for a supersingular elliptic curve. Now, you don't need this for the attack, but I think it's kind of, for the more broad setting, it's interesting to know that this doesn't generalize in an obvious way, because all of these different characterizations mean something else in higher dimensions. So in elliptic curves, you basically have ordinary and supersingular. But as soon as you go to dimension 2, you have ordinary, still ordinary, which is the same definition really. And then supersingular breaks down into supersingular, very special, and super special. As soon as you go to dimension 3, there's 8 different characterizations, and it just keeps growing and growing. So the question is, for cryptographic purposes, what do we need, and which of these definitions do we need? Well, the word supersingular in a more broad sense, really, so in higher dimensions, is not enough for cryptographic purposes. We want the strongest generalization. We want super special. Super special implies very special. It also implies supersingular and so on. It's the most restrictive of the one, because a product of supersingular elliptic curves, so seen as an abelian surface, as super special. The properties it has is that it also, all of the super special abelian surfaces are defined over fp squared and so on. So this is really the correct generalization that we want to use. So in that case, supersingular elliptic curve isogeny crypto, in higher dimension, it's super special abelian variety crypto, I would say. Okay, now something to come back to the question about, what was it, about the graph, etc. I think this may give a little bit more insight already. So in 2-dimensional, you also have invariants, right? So in the elliptic curve, you have a J invariant and a product of elliptic curves, and then defined by a set of J invariants. Why a set? Well, if you have E times E prime, that's in a very obvious way isomorphic to E prime times E. So you can't really put an order on this. I mean, it doesn't make sense. They're just isomorphic, right? However, a genus 2 curve is defined by a triplet. I think the word in English is triplet. So that's a type of Igusa invariants. There are longer change, but I think the absolute Igusa invariants are an ordered triplet. So there's 3 invariants there. Okay, and these definitely have an order. Now, what most of you will probably know is that there's P over 12 supersingular elliptic curves with some error term epsilon, whatever. Now, if you want to have a product of supersingular elliptic curves, then that's a super special abelian surface. Then there's P over 12 options for this one, P over 12 for that one. However, we counted it twice. So in total, there's P squared over 288 super special products. Again, this is approximately, but we're working with cryptographic P, so like lower order terms of plus P over something don't really matter here. Now, if I would ask you how many, well, no, I don't want to ask this, but basically there is P cubed over 2,888 super special Jacobians of genus 2 curves. So that's quite a bit bigger, right? In a similar sense, that's also like the question that was asked before. This is a subgraph of the entire abelian surface subgraph. If you just look at nodes, we haven't really defined isogenies in dimension 2 yet. And these make up a very small portion of it, right? Like a dimension lower. So this is like P squared. You can look at the amount of super special products of elliptic curves as like the, how do you see that? Like the sphere. Whereas like the amount of super special Jacobians is like the interior of the sphere, right? Or something like that if you want to envision it in 3 dimensions. Now the thing is, like just pointing out, we have this amount and this amount, but again, this only works with principally polarized abelian surfaces because the answer to how many, up to isomorphism, of course, all of this is defined. If I were to ask how many super special abelian surfaces exist without using the term principal polarization, then the answer is 1. Everything is isomorphic to one another. There isn't, not that I know of. Somebody asked if there's an intuitive explanation for the P cubed over 2,880, sorry. Not that I know of. I mean, just like proving the theorem is kind of hard. There's definitely one of the papers like this about the genus 2 hash function that I can't name the reference where I can easily find a proof, but it's not. Yeah, it's not. It's definitely not easy. I don't think it's intuitive. Maybe intuitive for some mathematician is the growth of it. I think if you go to dimension 3, then it's the order of magnitude is p to the 5th. I think it's something like that. I think it's like p to the power 2g minus 1 or something, with some constants, but I don't know where the 2088 comes from or anything. But yeah, the most important thing is that there's definitely a lot more of these, right? I mean, that's something that we'll have to keep in mind for the future. And it's also like where the initial angle for the attack came from. Okay, I think we're ready to sort of define isogenies in dimension 2. There are different types of isogenies, but I'm going to focus on the most natural generalization of what people are used to in dimension 1. And these are called NN isogenies. For elliptic curves, you typically talk about an N isogeny as being a cyclic isogeny of degree N. Now we talk about an NN isogeny. It's no longer cyclic because there's 2 copies of Z mod N. That's fine. But we need an extra condition. This condition for elliptic curves is trivial, so it's omitted always, but it still applies if you want to be technical about it. And it means that the kernel is maximal isotropic with regards to the N while pairing. So for all the points in the kernel, it means that the while pairing is 1. Okay, why do we need this? Because this ensures that whatever we land on here comes equipped with a natural principal polarization. Because otherwise, we're again not necessarily working with a principally polarized Abelian surface as a codomain, and I mean, at that point, things get funky. You can still define that, I guess, but the polarization is gone here. But from an abstract point of view, it's still an Abelian surface. It's just, well, I mean, it's not as easy to do computations with or on it. But yeah, this is the most general or natural generalization. It's not super hard. I mean, this is a technical thing, but this is just instead of a cyclic isogeny, you just have like, I don't know if bicyclic is a word, I don't think so, but you just have 2 generators for the kernel now instead of 1. Question. This pairing condition isn't always true for elliptic curves. In what sense, Lorenz? Hold on. Was it not trivial? What type of isogeny are you talking about? I mean, well, N isn't prime, but it's well, yeah, if you do like a scalar multiplication as an isogeny, then this is obviously not true. But I'll go back here, for example, if you would replace, like for example, you can also have a scalar multiplication isogeny. In that case, it's just N, 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 N. So you kill all 4 copies of Z mod N, because the N torsion is now, instead of 2 copies, it's 4 copies. And in that case, it's obviously no longer maximal isotropic. So something similar happens as well in elliptic curve cases where you can, okay, yeah. So for elliptic curves, this is still true, but obviously you have other isogenies. So in particular, you can also have like, let's say N squared and N isogeny, where again, this is not necessarily true or something. But these are the easiest ones and the ones we're going to be working with. WRT just means with regards to the N while pairing. Okay. So Benjamin Izolowski has a comment that it's also true for the scalar multiplication because En is isotropic for the N squared while pairing. Okay, yeah, that's true. Okay, curious now. Well, obviously you have Frobenius and stuff, so there are some exceptions, but scalar multiplication was not really a good example of me to say that it's an exception to this rule. Okay, cool. Thanks. Any more questions? Again, this has to do with principal polarization, which I'm not going to go into, but as long as you just envision now, like, okay, we have 2 generators for a kernel, then we're good to go, really. So we have 2 types of Abelian surfaces. We have 4 types of isogenies, right? We have domain and a codomain, and we kind of want to We can go from a Jacobian to a Jacobian, we can go from a Jacobian to a product, or vice versa. I mean, this is really just a dual setting, or we can go from a product to another product. And this is in a way like, I can come back to the connectedness now of the, or at least very soon, to the connectedness of the product of elliptic curves subgraph. Now, most of the abelian surfaces are Jacobians, as I said before. In the super special setting, it's p cubed. So if you take an arbitrary abelian surface and an arbitrary n isogeny, like with overwhelming probability, you have like the first case, right? So this, I don't think this has a specific name, but this is very generic. And n isogeny, I think mathematically this is rather well understood. Computationally, it's different. For n equal 2, we have Richelieu isogeny, also like a recent paper by Sabrina, last name Kunzweiler, I hope I pronounced it correctly, which speeds something up. Those are efficient. You also have 3-3 isogenies that are fully parametrized by Bruin, Testa, and I apologize, I think there's a third name. Those are somewhat efficient, but if you want to like push a point through that isogeny, like the equation for that is Bruin, Flint, Testa. Okay, sorry, Bruin, Flint, Testa. Then the equations to push a point through a 3-3 isogeny is like, I'm talking kilobytes already, so that's quite a bit different than like the one line you can pretty much assign to a 3 isogeny and for elliptic curves, right? In general, for higher n, if n is not prime, same thing applies. You can decompose it into prime isogenies as long as you can factor n, of course. And I think the state of the art is still the paper from Cossain Robert from 2015 to compute LL isogenies. It's highly inefficient in the sense that if you would try and instantiate C-side with that, I don't think a key exchange would finish in a week. But then again, I think like nobody ever really tried to, well, I think the work from Cossain Robert is like, I think it's cool, but I don't think like computationally wise, a lot of people have tried to optimize it. But it's a lot harder. It's a lot harder. So in theory, our attack generalizes, but like actually implementing it for SIDH, where you don't use the 2 or the 3 torsion, would be quite different. But 2 and 3 is fine. That's well researched. Okay. After that, we can also start from a Jacobian and then go to product of elliptic curves. This is called a split n Jacobian, sometimes also called a split isogeny. I kind of like the name. It makes sense. What if the points are in the algebraic closure? I'm just assuming that we work over the algebraic closure. For type 2, nothing really changes. It just, I mean, if you actually want to compute it, it just makes it harder to compute even. So there's no real distinction to be made there, at least not from our perspective right now. So this will not happen too often, right? Because there's few products of elliptic curves. I think the most concise, or however you want to call it, characterization of this is by Kuhn. So what typically happens here is you don't really look at it from an isogeny type of way. What you do is you project the genus 2 curve C on the projective line. So you look at the Kummer line, basically you work with X-only arithmetic. You do the same with E1 prime and E2 prime. And then you can construct 2 distinct morphisms from the projective line here to one here and another one there. And those morphisms have degree n. And then like this lifts in a proper way. If you want to read about it, I think it's cool. It mostly works with the ramification of the Weierstrass points, etc. And even and odd is quite different. So as I said, Kuhn, I can give the reference. If people like want it, I can give it in chat after or something. For 2 and 3, this is well understood and well explained. Again, from 5 onwards, there's no real parameterizations anymore either. Things are somewhat complex, not impossible. But I don't think there's been a need ever to write this down. But some general methods can apply. I think like Kuhn's work gives enough things to actually like implement it if you really want. Now, the dual isogeny of this is like you glue elliptic curves along their n torsion. Again, I kind of like the name as well. And generically, this is also what you expect to happen, right? If you take a product of elliptic curves and you take a random n isogeny, you would expect like most of the abelian surfaces are genus 2 curves, or at least Jacobians of genus 2 curves. So you expect this to be more common than situation 4. That's true for all cases except n equals 2. There's where fourth one is more common. So that makes sense. We'll go into depth about this one. But the last case is sort of a rare case, right? I don't think this has a specific name either, but it's just an n isogenies between products of elliptic curves. And that's really it. So we have 4 cases, and we're going to sort of focus on the last and the third case here. Now, if I were to ask you, can you guys write down, like people who are familiar with isogenies but not familiar with genus 2 or 2-dimensional isogenies, can you write down an isogeny of the 4th type? Then I would say yes, most of you will. Just take 2 cyclic n isogenies in 1 dimension, and then the product isogeny is simply component-wise. It's like you go from E1 to E1 prime, you go from E2 to E prime, boom, you're done. This is an n isogeny from a product of elliptic curves to a product of elliptic curves. Very boring, but for n equals 2, there's 9 of these, of the total 15 2 isogenies. So this is the only case where there's more of these than of the type 3. Now, why does this work? Well, because, well, simply, I mean, it's a bit technical, it doesn't matter much, because the n-wild pairing on the products is equals the product of the n-wild pairing. So the second condition in the n isogeny is satisfied, and everything behaves very as you expected and very, well, in a boring way, I guess, but it's still like an example. So this kernel of this isogeny can also be written down as P with point at infinity and then point at infinity Q, where P obviously is a generator of the kernel of phi1 and Q is a generator of the kernel of phi2. So in that sense, somebody asked, like, is this subgraph connected? Well, like all super singular elliptic curves are connected. So you can go from E1 to pretty much any elliptic curve, super singular elliptic curve you want, right? And from E2 as well. So if you would only look at these isogenies themselves, I would say, unless there's something I'm really, at least conceptually, I think this is a connected subgraph of the abelian surfaces graph, if you would only consider these types of isogenies, simply because the super singular isogeny graph is connected as well. I mean, there may be some technicalities, but I don't see why it shouldn't be connected. Now, the more interesting case is like, okay, yeah, this is called a diagonal kernel. I'm not sure how, I've only seen this mentioned a couple of times, so I'm not sure how standard this notation is. It stems from the fact that this also applies in higher dimensions. So obviously, if you go in dimension 3, then you have PQR. If you write it in some sort of matrix, then obviously only on the diagonal you have. Okay, Enric Fluid says there's a technical point on tensor product graphs, but it should work for all n. Yeah, okay. I am happy with that answer, because yeah, there's some technicalities that you need to take care of, but it should behave as expected. Okay, so this is called a diagonal kernel because, well, you work with the trivial points on one hand and then on the other on the first curve. Obviously, if there's a diagonal kernel, there's also a non-diagonal kernel. So what does this look like then? Well, the kernel of like an isogeny like this is then generated by 2 elements of the n torsion, right? So P is an n torsion point on E1, Q is an n torsion point on E2. So this pair of points, somebody asked earlier what a point looks like on this product, is then an n torsion point on this abelian surface. And this is also an end torsion point on this abelian surface. And together they generate the kernel, and then you end up in a new abelian surface. The big question is now, like, when is this product of elliptic curves and when is this not? Like in general, like as I said before, like for super special abelian surfaces, if you just take heuristically a random or an arbitrary abelian surface, this is almost always going to be the Jacobian of a genus 2 curve, right? I mean, with probability only 10 over p, which is absolutely negligible, this would be a product of elliptic curves. I mean, even more so if you just saw my previous slide, it's like, oh, okay, we have already had a bunch of like codomains that are a product of elliptic curves, so this is probably even less. The odds are even less. I mean, asymptotically they're not, but still, we've already covered a bunch. So when does this fail? I mean, the thing is, both situations occur, and like when the clue in our SIKE attack is really exactly when is A prime a product of elliptic curves. Okay, are there any questions about anything I've mentioned before? I'm gonna check the time, probably gonna be, okay, it's already 6 o'clock, wow. I apologize, but it's gonna be on YouTube if people have to leave. But I still have to actually start talking about the attack. Okay, no questions. So then we're going to go to the glue and split attack. So just to give you a bit of an intuition, some examples for failed gluings, like a 2-2 isogeny can only fail if E1 and E prime are isomorphic. And I mean can because there's still some technicalities that you need to take care of. The isomorphism needs to behave in a certain way. So like this is a necessary but not sufficient condition. A 3-3 isogeny can only fail to glue like this if there's a 2 isogeny existing between these elliptic curves. Okay, now like the people who are a bit like know a bit about isogenies, so like, well, an isomorphism between here, that's just a 1 isogeny, right? An isogeny of degree 1. So a 2 isogeny can fail if it's 1 isogenous, the elliptic curves. You can take like a 3-3 isogeny can fail if like they're 2 isogenous, right? So you would say like, well, at least for the primes, it's to be expected that 5-5 isogeny would fail or can fail if they're 4 isogenies, yes, but also 6 isogenies for some reason. So it's a little bit trickier than that. If you go further, 7-7 isogeny can fail to glue if it's 6, 10, or 12 isogenous. Again, necessary but not sufficient condition, and so on. And so for the composite, and it's even more delicate, and we'll talk about it a little bit more. But there are very specific conditions that say when the gluing can fail, but it's non-trivial. And yet it's been known for 25 years, right? Connie's theorem. So Connie's theorem, highly informal. If you want to read the theorem, go to Connie's paper, go read our paper, I guess. And then end gluing fails if and only if, which is quite nice. That's an if and only if. It's a very general statement, so he covers all the possibilities. It comes from an isogeny diamond configuration. You're probably thinking like, what the hell is that? Like that doesn't really give me any hope of like understanding it more. An isogeny diamond configuration of order n, typically it's called, is a tuple that consists of an isogeny and then 2 subgroups of its kernel, and those subgroups have to like satisfy some conditions. So 3, 4, and 5 are the conditions that these first 2 need to satisfy. Okay. So we're really interested in looking at when does this gluing thing fails to attack SIKE. So one thing, what do I mean by if it comes from an isogeny diamond configuration? So if you take this psi here and then some scalar multiple x there, this is basically the gist of Connie's theorem. So like if you have an isogeny diamond configuration, then you can construct some x here, and then this will be the kernel of an n isogeny starting from a product of elliptic curves that happens to end up having a codomain product of elliptic curves again, right? And this is obviously a non-diagonal kernel, so this is really the exceptional case. and it doesn't really happen frequently. Okay, now remember, going back to the SIDH setting for a bit, we're trying to attack Bob's secret key. What do we mean by fail? You fail to, if I talk about, well, failing is maybe a bit weird word. So what I mean is, and gluing basically means we try to compute an n isogeny starting from a product of elliptic curves. We expect it to go to a Jacobian, but the codomain being a Jacobian fails. So instead of gluing, we sort of like the glue didn't stick, and we just end up in a product of elliptic curves again, I guess. So by failing, I mean we end up on a product of elliptic curves again. And this subgroup is in Connie's theorem, by the way, for people who have read it, is like the reducible subgroup. It's called then. It's slightly differently phrased, but it really boils down to exactly this. So when I talk about the gluing failing, I just mean like we end up on a product of elliptic curves. Okay, so in SIDH, we're going to attack Bob's secret key. Why, I'm going to talk about it in a bit. But remember that we are given this as public parameters, at least. We are also given Bob's 3 to the F torsion generation, but we don't care about that for now. And we're also, like, as an attacker, we're like Eve, like the eavesdropper who is aware of like Bob's curve that he sends to Alice, as well as these torsion points. And we want to find Bob's secret isogeny, right? Okay, so again, this is the 2 to the E torsion basis, and this is an isogeny of degree 3 to the F. We call that. Now, as before, there's like the computational versus the decisional thing. In general, like the similar thing as before will apply. We'll, like in our attack, what we did was we reconstructed his isogeny piece by piece. We just had 4 options for Bob's first step in his isogeny chain, where he changed F isogenies of degree 3, 4 options, and we checked, okay, which one of the 4 is correct, which one of the 4 is 3 to the F minus 1 isogenies here. Okay, and we're going to do that. We're going to try to force this setting into an isogeny diamond configuration as before. So first question is, okay, I'll go back here. Can we force E1 and EB into some sort of isogeny diamond configuration? Because in the end, we kind of want to see if these are 3 to the F minus 1 isogeny, or at least which one of these. Can we do that? Yeah, I mean, first of all, the reason that we want to attack Bob's secret key is that once we will start checking this NN isogeny, so the failing of the gluing that I was talking about, then it's easiest to do that if we work with the 2-2 isogenies. So in dimension 2 as well, you have a 2 to the E, 2 to the E isogeny. That's simply a concatenation of E isogenies of, well, I can't say degree 2-2, but just you concatenate E 2-2 isogenies, which is the easiest thing you can do in Genus 2. Like, you could also attack Alice's key. 3-3 isogenies are still fine, but anything over that is harder. So in this definition, we're definitely going to want to replace 2 to the E, N with 2 to the E from earlier, because that's the easiest thing we can compute in dimension 2. And then the next thing is like, okay, so what shall we do here, right? I mean, like, we want to know the secret, so we don't really have this isogeny, but can we choose this one, perhaps? So if we choose this in the isogeny diamond configuration, if we replace E by E1, or like we have 4 options, right? But an attack with a factor of 4 is negligible. And then E prime can be EB, that's fine. So what would this give? Well, the degree of this isogeny would be 3 to the F minus 1, if we have chosen the correct E1 at least. If the incorrect ones will have degree 3 to the F plus 1, because we go through E0 and then can go back, I guess. But that's not relevant. We're just assuming we have the correct one for a bit. Okay, so, but like G1, G2 need to be subgroups of this kernel, right? So there will have an order like a power of 3. But then this sort of sucks, right? Like, to make this work, like 2 is not divisible by 3, so like these cannot both be divisible by 3, obviously. So then G1 would need to be 3 to the f minus 1, and then G2 would need to be the trivial group, just a neutral element, and then we would need to have that 2 to the e is 3 to the f minus 1 plus 1. Like, obviously, this is never true, at least not for cryptographic size things. I think the highest that for which this is true is like 2 squared is 3 plus 1, and it stops there. So we can't really do anything with this. But we can force it in a different way, but we cannot do it directly. We will start from E1 and we'll construct an isogeny gamma to some arbitrary curve C. Curve doesn't really matter. I mean, obviously they're isogenous, so we're going to stick in super singular elliptic curve land. And we want the degree to be C equals this. Okay. First question, is C bigger than 0? Well, I mean, maybe. The thing is, if it's not bigger than 0, then we can just switch the roles of Alice and Bob at the very least. We're going to have to compute like 3 isogenies, but that's fine, right? Because then the 3 to the f would be here, and then you had 3 to the f minus 2 to the e minus 1. So this doesn't matter too much. In any case, if we would try to start from E2, then we would have 2 to the e minus 3 to the f minus 2. So we can lower this exponent if need be, which is what we've done in practice. And we didn't switch to Alice's secret key. But this is a small hindrance, but technicality, because the degree has to be positive. How do we construct this? Well, we'll talk about that later, but just assume now very vaguely that we can do this, okay? What we will then do is we'll define this isogeny diamond configuration of order 2 to the e as a tuple consisting of this isogeny. Basically the phi 1 that we had from earlier, starting from E1 with codomain EB, but pre-concatenated, I don't know, with a dual of gamma. So we start from C to EB. Okay, now why do we pick this? Well, we can then pick G1 to be the kernel of the dual of gamma, and G2 be, well, like, again, we want to find the secret, right? So we don't really know Bob's secret kernel. However, abstractly, we, like, if we guess the correct E1, we sort of know what it is, right? We also don't really need to know what it is coming from C, because we can compute this entire chain, right? If we can compute gamma, we can compute the dual of gamma, and like phi 1 is a thing we sort of want to guess, but we have only 4 options, so one of them will be correct, right? So if we split it like this, well, gamma has, the dual of gamma has degree C. Obviously, this is co-prime with the degree of phi 1, because this is a power of 3. So they intersect trivially. This is fine for the definition of isogeny diamond configuration. The degree of psi will then be, well, the degree of phi 1 times the degree of the dual of gamma. And the main reason, obviously, like I'm guessing some people already know this or notice, is that if we take C to be this, then obviously 2 to the e equals 2 to the e minus this plus this. Right, this is the main reason that we're really interested in taking this specific degree C. Okay, so we sort of constructed, assuming for a second, like that, like a black box, that we know how to construct an isogeny of this degree. We have an isogeny diamond configuration constructed. I mean, it's like in general, they are rare if you just look at the general n isogeny graph, but you can construct them. If you do a little bit of work, you can actually construct them the way you want. And if now, like, so I'm going to go back here. So we have an isogeny C going through E1 and then EB. But in general, this means that we can consider the product of the curves, C times EB. So this is from this auxiliary isogeny gamma. This is the Bob's elliptic curve that he sends to Alice. And then we have codomain that we're not really sure about what it is yet, an abelian surface A prime. And then with Connie's theorem, it basically says gamma PA and phi B of PA and then gamma QA, phi B of QA as well. This generates a kernel of an isogeny. Everything is fine. Like you need to do some, you need to check the maximal isotropicness and so on to have the principal polarization. But this is fine. This is a kernel. Obviously, like these are points of order 2 to the e, and the degree of gamma and phi b is co-prime to that. So in practice, if we want to compute this isogeny, this is very simple. This is just like a concatenation of e to 2 isogenies, right? So this first is a regular to-2 grouping. I mean, the chance of this failing is non-existent because then C and EB would be isomorphic. And in general, like in practice, this never really fails. We've noticed this as well. You never encounter a product of elliptic curves along the way, except for the last one, obviously. The clue of this entire thing is we constructed this way. And if you notice that A prime is a product of elliptic curves, that means we picked the correct E1. And as it says with overwhelming probability, because really we never noticed it, like there's 4 options, right? For first choice for Bob, and then for subsequent EIs, there's 3 options. But at no point did we ever encounter that, like we by chance constructed a different diamond configuration. That just doesn't happen. It's so rare. Chance 10 over p is like what you heuristically expect, but I think it can be argued that maybe it's like not possible even. So as soon as you compute these 4 options, like one of them will end up in a product of elliptic curves, and then you have found the correct E1. And that's it, then you have found the first step. You can do the same for E2, but now you have less options. You have 3 options basically, then for E3 again 3 options, and so on until you recompute the entire isogeny chain. So hence the name glue and split attack, because, well, you first glue them together, then you do some regular isogenies, and then you see if it splits. And if it splits, you actually won. You actually found a piece of information. And if you end up in a Jacobian, well, yeah, then tough luck. Then then one of the other options will yield some results. Okay, so now something that we've really swept under the rug so far is finding such a gamma of degree C 2 to the e minus, well, like obviously at different steps, like you first need to find E1, E2, and so on. So instead of f minus 1, this generalizes to f minus I, right? Because we need to solve the decisional problem for all these I, or at least as many i's as possible. Now, if your curve EI would happen to be this curve, for example, this has a really cool and small endomorphism I, just maps xy to minus x and then square root of minus 1y. This is a very small endomorphism. And in general, if C can be written as a sum of 2 squares, you can decompose it as this. And basically by replacing this I by iota and these U and V by scalar multiples, then you can pretty much, instead of taking an isogeny gamma, you can even specifically take an endomorphism gamma, where like you start from E1, EI and go to EI, and you just do something very, very quickly as an endomorphism on EI itself. How often can you write this? This is where I talked about integer factorizations that need to be pre-computed. You can write this specifically as a sum of 2 squares in integer if and only if it factors into prime factors which are all equivalent to 1 mod 4. This is sort of a restrictive thing, I guess, because this is obviously not always the case. But as I said before, even if this is not true for I equals 1, it can be true for I equals 2. So there's definitely enough in that sense, but I'm going to talk about some tricks further up ahead where this isn't even needed to do this anymore. Okay. Now the starting curve in SIKE, as I said before, is this one. It's a similar trick. This has endomorphism 2 iota, which shouldn't be too surprising given that this one is 2 isogenous to this curve. It's a similar it's actually the exact same trick. We actually use this curve, this endomorphism on this curve to generate the isogenies of degree C. And you can actually translate this small endomorphism, so this degree C isogeny on E0 to whatever EI you want. Technically, it's not even needed. I forgot who mentioned that first to us. Some people pointed it out, that so you start from E0 in SIKE, and you want to construct the isogeny chain E1, E2, E3, E4, and so on up until EK, right? So what we did in practice in our implementation is that, well, computed E1, E2, and then we always checked if E1 was 3 to the F minus 1 isogenies with E prime and EB, sorry, and we pushed it that way. However, you can also try and compute dual isogeny, obviously, so you can start from back and chip off degree 3 isogenies there, because then you can just reuse your gamma 0 on your starting curve. So that would have been smarter, I guess. I mean, I'm not sure implementation-wise how much it would differ, but then you don't have to translate the small endomorphism to whatever step you're working on. Apart from that, there are other supersingular elliptic curves. So like y squared equals x cubed plus 1 has a small endomorphism of degree 3. That's okay too. You can do something similar. And in general, if you know the endomorphism ring, you can use the KLPT algorithm. I'm not sure how much overhead that would give. We never had to implement it because, well, SIKE starts from this elliptic curve, so we didn't need it. But in theory, at least, this just works just as well, right? This is only if we know an endomorphism ring. There's no way to hash into the supersingular elliptic curve graph, in the sense that if you want to write down a supersingular elliptic curve, then there's always a way to know the endomorphism ring. So you can't like write it down. However, there's still constructions, maybe with a trusted setup or whatever, where you generate a supersingular elliptic curve with an unknown endomorphism ring. What do you do then? Well, first of all, you hope that C is smooth, right? I mean, the specific isogeny for the diamond configuration doesn't matter much. You just need it to be degree C, and you need it to be computable. So if you're very lucky and like for I equals 7 or whatever, this is a smooth number, you can still do our attack. But you're going to have to work over extension fields, and you're going to have to work with isogenies of degree, the factors of this integer, obviously. And in general, like for cryptographic sized E and F, this doesn't work. But there's some leeway. Instead of looking at just integers of this form, you can look at integers of this form and hope that they are smooth. So there's like 4 adjustments. As I said before, we don't need all the steps in the isogeny chain, as long as you have like the biggest ones are the most important ones, or the hardest ones, obviously. So the small I, like I is 1, is typically the hardest one, but you can lower it if you only can compute E10. If it's 3 to the F minus 10 isogeny to the ending curve, then that's fine as well. It just gives a lot more options for the first one, right? Then you need to check 3 to the 10th options, which is not ideal, but you can do that. Secondly, if you start enlarging I, that means you have more leeway to keep this positive, and you can lower J, because if we know the action on the 2 to the E torsion, we also know the action on the 2 to the E minus J torsion. That's a given, right? You just scalar multiply with 2 to the J. This gives some more leeway again, and this is also what you can do if you know the endomorphism ring, and if it doesn't factor into primes which are 1 mod 4. You can also do it like this, because the further you are in like reconstructing the entire isogeny chain, the larger I is here, and the more options you have for J here as well, right? And heuristically, only very few steps in the isogeny chain didn't have some option C, which factored into primes 1 mod 4. And then these other 2 like integers D and D prime. Well, D prime, what like this equation, what does this mean in terms of isogenies? We can extend phi B with any isogeny of degree D prime as long as it's computable, right? I mean, because like this integer C is expected to be very non-smooth in general. Maybe if you add something smooth here, then this is also smoother. at least. So as long as D prime is as smooth as C, this is a good thing to try and do. Keep in mind though, especially if I is small, you have very little leeway here, because C, if you take a D prime which is large, then this integer will no longer be positive, right? And then the final adjustment that you can do is this D. What does this D mean in terms of isogenies? Well, like you can still do the attack with all the adjustments, and then you have like 2 to the A minus J, 2 to the E minus J isogeny, which will always be a Jacobian, or with overwhelming probability, you'll end up at a Jacobian of a genus 2 curve. And then at the last step, you sort of need to check, oh, okay, give me all the DD isogenous neighbors. Does one of them, is one of these abelian surfaces a product of elliptic curves? Now, keep in mind, this has to be done over an extension field. And even over non-extension fields, computing DD isogeny is already sketchy. So pushing this, I don't expect this to be possible for very large D. I think like D, anything over 100 would computationally already be very hard. Not because, well, you have to first compute a DD isogeny, which is quadratic in the best case in D. You also need to go over an extension field with maybe like of order fp to the 2D then. But also you need to check all the DD isogenous neighbors, which is again cubic in D. So there are, well, asymptotically D cubed DD isogenous neighbors if D is a prime. I mean, it's more complicated because D is a composite number. But this still works in theory, at least, because the probability that that one of these DD isogenous neighbors is a product of elliptic curves is still D cubed over P. Again, D will never be, D cubed even will never be close to P. So the probability of this happening is very little. I mean, we didn't implement it yet because I think in practice, this is really hard to attack SIDH with. But in theory, at least this should also work. We have some leeway, and well, you can adjust as you want. I mean, even finding smooth solution to this is not really a trivial task for the parameters that SIDH works with. I mean, at first sight, I wouldn't even know how to generate possible D, D prime, J, and I to make this as smooth as possible in like I want to say in an efficient way. But anyway, these are some tricks that you can do if the endomorphism ring is unknown. Although Damien Robert kind of killed the need for this idea, I guess, where he had a polynomial time attack in 8 dimensions, even if you don't know the endomorphism ring. But at least this part, like the 2 to the E minus J, we sort of used in our attack as well. So there are some parameters that you can toy with. Okay, I'm going to look at the time, and I'm going to just finish because it's way past time. So I want to say thank you for your attention, and I hope it was clear. I'm fine to answer any possible questions for the people who are still here.
Thank you, Thomas. I think it was a very enlightening talk. If anybody has any questions, you can just turn on your camera and raise your hand, or unmute if there aren't too many. And then,
or chat is fine as well.
Or in the chat. Chat is also fine. If nobody has a question so far, I have a small question that I was very curious about. Mm-hmm. Did you just run into Connie's theorem, or how did you end up in that position?
Well, at the original idea, I rewatched Wouter's talk at ANTS recently, and he mentioned that there as well was to actually make something constructive out of this. And we were really curious, like where it failed. And then we also had issues with like checking polarizations. And when Luciano, I don't know how to pronounce his last name, Maino, sorry, I think he's here, was in Leuven visiting, we sort of picked up that idea to do something with that. But we ran into issues with polarization mostly, because that's, I mean, it's something technical. You can write down like with symbols, so without any equations, just points, you can write down things that look like an endomorphism on a product of elliptic curves, but then like once you try to implement it or once you start working on it, it's like, okay, yeah, we lost our polarization. So the codomain is like, can be anything, or at least you don't know what the hell it is, or you still need to polarize it, or you need to find another isogeny. And then we sort of came into Conning's theorem, which pretty much exactly, I don't know where it was referenced. Yeah, I don't know what paper referenced Connie's theorem, but it referenced it and it's like, okay, this solves everything pretty much. This solves the polarization, and then it also said like, oh, okay, but you also sort of, you can sort of construct, I mean, hold on, I need to minimize this. Sorry, I'm gonna go back. The original thing was like more of like this, right? I mean, you can, an LL isogeny, you can make it sort of to fail, like if E1 and E2 are L-1 isogenous, you can make this fail. I mean, that's always true. There are other options from Connie's theorem. But that was an interesting idea to us, because nothing like this exists in elliptic curves, right? In elliptic curves, like if you have an isogeny of degree 2 and 3, they have nothing in common. Like even if you look at a supersingular 2 isogeny graph and a supersingular 3 isogeny graph, like if you have an isogeny starting from E1, which is of degree 2, and then of degree 3, then like the codomains will have nothing in common. You can't translate that into one another. But as soon as you go to dimension 2, a two-dimensional isogeny, like an LL isogeny, you can translate that to something which is completely co-prime to LL, which is a pretty cool idea, right? And then like we started working on that, and I think like the L-1 thing is mentioned in a couple of things. In particular, these two are actually explicit in a couple of papers. And then Connie's theorem basically said like what the extra conditions have to be, because for 2, 2, and 3, 3, they're very minimal and very explicit, so you don't really need to worry about too much. So that was the initial thing, and then, well, Connie's paper has been cited dozens of times, which kind of surprises in hindsight that nobody actually found this in a way, but like hindsight is 2020, obviously. There are some questions in the chat as well. Yeah, I'm sorry, unless like my answer wasn't clear yet.
No. I'll go to the answers in the chat, because there's one hidden by Lawrence between the compliments. What did you do with the 50K from Microsoft? A
good question. We are still in the process of having it gifted to our university, and we have no, I mean, like, yeah, Microsoft contacted us, like, we are working on getting the funds, but like officially it says in the Microsoft bounty terms as well that it's a gift to our university. So what happens with the money? I don't know, we're happy with the result as it is. The money is like, okay, it would be cool, but whatever, you know. But we'll see what's possible legal. Could you please recommend some literature about Jacobians and Abelian varieties? I think there's a PhD thesis that I think that Brock's, I forgot his first name, Brock's thesis, hold on. It talks about super special Abelian varieties more generally, I think, which is kind of a nice thing to read if you're interested in Abelian variety crypto. I would need to look up the name. Hold on. Is there any next question? I'll do it as quickly as possible now. The next question is there anything similar to Connie's theorem to maybe find isogenies? The other way around is basically the dual. The question is, oh, that's a good question. So the question is, when does a Jacobian NN split would be your question, right? there is, I think Martin Jukanovic has some sort of algorithm that does it, but I'm not sure how high you can push it. The thing is, in 2-2 isogenies and 3-3 isogenies, the 2-2 split and 3-3 split are very explicit. It's basically some algebraic expression. For people who know Richelieu, isogenies is basically small delta being 0. For 3-3 isogenies, it's capital delta being 0. So I sort of think that it's possible that there could be an algebraic expression in the coefficients of C, which is easily expressible, that can make a decisional version of the does this n split. That's something that I think is possible. And the best of my knowledge, the Martin Jukanovic PhD thesis, chapter 1, has some algorithm for that, but it uses like a Grübner basis, which has, I want to say, 3n/2 variables, so that kind of will scale really badly, I think. But I'm pretty sure it's implementable for smaller n, but definitely like n 5, 7, 11, 13. Keep in mind, like if n is composite, changes things a bit, because then the best case is to just do an LL isogeny and then check the prime splitting. Yes, sorry. Super special curves of genera 2 and 3. Some stuff is in there as well about the very special, super singular, super special, etc. Apart from that, Jacobians and Abelian varieties, I don't know, like my knowledge about that has been from bits and pieces everywhere. I can definitely recommend Ben Smith's thesis for Richelieu isogenies as well, which has some stuff about polarizations. So his name is Benjamin Smith. His PhD thesis was endomorphisms and correspondences or something, but I'm not entirely sure about that. There's also a nice thing I remember in a master thesis I had to do for some course, something about Jacobians, for which I recycled the picture for the geometric construction at least, but I really can't recall that name. So yeah, I'd say Brock for the super special ones, and I like Ben Smith's thesis. I've definitely referenced it multiple times throughout my PhD.
Thanks. I don't think there are any more questions, so I would like to thank you again for kicking off the Isogeny Club with a great first talk.
Okay, you're welcome.
Bruno is, I think, also still here. Maybe you can turn on your camera if you want to. Bruno will be giving the talk in 2 weeks at the same day and at the same time. And his talk is titled Git commit -m isogenies.
Okay.
And it's about the properties of supersingular isogeny graphs that make it an interesting object to study, and how you can create a commitment scheme from this. So I hope to see many of you in 2 weeks again for Bruno's talk. And with that, I think we can end the first session of the Isogeny Club.
Apologies for going so much over time, but there were some interesting questions and some discussion from the audience as well, which I liked.
I think everybody was fine with it.
Agreed. But much better to keep it a bit more dialogue, right? But
Yeah.
Thanks so much, Thomas. Great talk.
You're welcome. I enjoyed talking about it and enjoyed discussing some things. And see you in 2 weeks.
The recording. Yeah, sorry, I'll just end the recording here.